Great, thank you, and thanks so much to the organizers for the opportunity to speak here. So I want to tell you a story that's been ongoing for several years and is picking up recently on our numerical capabilities for assessing some data of adjoint QCD2. This goes back to work with Loki Lin and Sylvia Pufu and Igor Klebanov, who are all here, and then some more recent work with Benjamin Sogard and a new thread with a new student, Anna Maria Gluck. So adjoint QCD2 is a fan favorite model of this collaboration. We'll take SUNC gauge group and couple it to a Majorana adjoint fermion. It's interesting for many reasons. One is that it's a useful toy model of confining and then deconfining gauge dynamics. When the adjoint mass is taken to be 0, then we have a surprising phenomenon where probe quarks are actually deconfined despite only having a dynamical adjoint matter. So this is one of many reasons this model is of great interest. And there's been lots of recent interest and progress, including from many people in the room. So several years ago, there was work on the non-invertible symmetries of this model and some really non-trivial predictions from that. Clay told us some more about even more predictions from that yesterday. Marie and Alexei computed RG flows, beta functions of some parameters you could add to this model. There was a Monte Carlo lattice setup due to Mitot and others. So lots of interest, lots of progress. And there are still important, even conceptual questions that remain open. For instance, Uwe told us yesterday about this very slight but non-zero dependence of various quantities on the number of colors. And so I'll say a lot more about that today. But overall, my focus will be what can we learn from the new tools we have at our disposal, the Hamiltonian lattice formulation, which several of us worked on a couple of years ago, and the powerful new tensor network methods that Benjamin told you about yesterday. So putting all these things together, we have a new story to tell about this theory. So despite that, I want to start by going way back to some of the earliest numerical work on this theory from several papers in the 90s by Igor and many collaborators. And this is using discretized light cone quantization to compute the spectrum of this theory. And so the process, in very few words, so we'll change to light cone coordinates, then quantize the theory with one light cone direction x plus taken to be the time-length direction. That allows us to integrate out all the fields of the theory except for one component of the fermion, so things simplify quite a bit. And then in the space-like direction, we'll compactify with anti-periodic boundary conditions, and so we can expand this chi fermion into these modes, which I'll call B. And so the question is, what can we learn from this? Well, we can fix one component of the momentum in units of the compactification radius. We'll call it K. Fixing this K to be finite will give us a finite Hilbert space. And so we can take this mass squared operator and actually put it on the computer, actually diagonalize it, actually get some numbers. That's for finite K. As we take K very large, we should recover the continuum spectrum of the theory. So that was one of the first things that was done to understand what's going on in this model. And so in the large N model, what you need to do to form the gauge invariant Hilbert space is to take gauge invariant combinations of these adjoint valued Bij operators. So the way to do that with large N SUN matrices is to form traces. And so the large N base shapes will be simple. We have these traces of these Bs. They obey some constraint due to our discretization and our cutoff of the momentum. And then we build those states, diagonalize a matrix to see what happens. And so it was done in the 90s. We did it again more recently. So here's one of the more recent plots where we pushed to the fairly high K. And what you can see here, there's many things going on in this plot. I won't talk about all of them. But what's happening is K is increasing to the left. And so that's where you should look at the continuum limit of the theory. And we can see this M squared in units of a Church coupling, G squared NC. We have clear trajectories coming out to a few bound states, a few particles. Colored them red for fermions and blue for bosons. So the lowest one is a fermion of mass squared 5.7 in these units, then a boson at 10.8, a fermion at 17.2, and then a two-particle continuum. Lots of neat stuff happens above that continuum, but I'll be focused below it today. So that's the spectrum at large NC. So great, we have that. What about at finite NC? How does the problem change then? So now we have a more complicated group theory problem. If we want to take these adjoint valued operators and again form the gauge singlet states that should form our Hilbert space. At finite NC, I have to ask, okay, if I take these representations, several 3s of SU2 or 8s of SU3, how do I stitch them together into singlets? And if you try to start from the large N basis, from these traces that we form these matrices, you can certainly still do that at finite NC, but you'll miss that some of them are secretly the same, or said another way, some combinations are null. So for instance, in SU2, this single trace combination of 4 B daggers is actually the same as a double trace combination, not true at any other NC, but true for SU2. And so we have to deal with this somehow if we want to do DLCQ at finite NC. And to give examples of how much of a problem this is, so take k equals 30, a pretty modest value. We have a few 100,000 states at large N, but then down to tens of thousands at SU4, thousands at SU3, only just over 100 at for SU2. So it really matters. These trace relations remove a lot of states. So how do we deal with that numerically? Well, one way would be to actually find the trace relations. This is something that can be done in a rather automated way. And sort of the algorithm is to take some relations of, say, sigma matrices for SU2, or the Gelman lambda matrices for SU3, or generalizations to higher SUN, and derive some properties that they obey, which are written in those examples here. These properties can be derived in a systematic way from the idea that a matrix obeys its own characteristic equation. So there is an algorithm of sorts to derive these relations, and then contract them with these operators and build a whole slew of relations, right? The hundreds of thousands of relations that you would need to carve out the finite N Hilbert space from the large N Hilbert space. But we can do this, and we did it for SU3, SU4. But I don't want to focus on that. I want to focus on a method that we use for SU2. Now that will be more relevant to the later half of my talk. And so this is using the invariant tensors of SU2 to build a basis of gauge invariant states there. So this is thanks to some great work by Loki Lin. What we can do is use these invariant tensors for the SU2 adjoint, which are simply the delta and the epsilon. And then we can take these B dagger operators, which I've drawn with thick lines that correspond to an adjoint index, and then bring these indices together using those invariant tensors. This is pretty simple, but the point I want to make is that contractions like these are going to be automatically gauge invariant, since all the indices have ended on some invariant tensor, and all gauge invariant states can be expressed in this way. So this is something we can do, and it makes things far more efficient if we do things this way. Of course, it takes some work, but then it's really worth it. Good. So using this method to construct the Hilbert space for SU2, we can do DLCQ again, and one might expect to find a whole new spectrum, because 2 is very different from infinity. There should be different things happening, but alas, it's actually quite similar. So you can see, if I extrapolate again, k to infinity going to the left, and then look at the mass squared of the bound states, the lowest 2 to this precision are just the same as they were at large N, again, when rescaled by G squared NC. So we have a 5.7 fermion, this 10.8 boson. The 17.2 is missing. That's just for kinematic reasons. There's no charge conjugation odd sector in SU2, so it couldn't have been there. But then otherwise things look roughly the same. So this is interesting. We can do it also for SU3 using those trace relations. A similar thing happens, and now the 17.2 has reappeared, and everything else is similar as well. So this is the surprising fact that when these things are rescaled by the Chilch coupling, finite NC makes almost no difference. So the first question you might ask after seeing these plots is, well, is there any difference? Could it be exact? Could these be the exact same 5.7 numbers that we saw in large N? Yeah.
Do you use the same trait for SU3?
Not for this, but for later work, I'll tell you about that. Yeah, that's right. Yeah. So as Uwe told us all yesterday, it's actually not an exact thing. There's just a very slight NC dependence. And so a way to see that from this method is to use this neat fact that the NC independence is not only true after extrapolating, it's true even before extrapolating. That's a key fact that we'll need. So I've used that fact here to say, okay, don't extrapolate yet. Just take the Hamiltonian at some finite k, take the mass of the lowest fermion at that finite k, and then take the difference between, say, the SU2 value and the large N value. And so this upper curve for SU2 is those differences, and likewise for SU3, 4, 5. And then after doing that subtraction at finite k, you can extrapolate to the continuum and get some estimate for how this fermion mass changes between, say, 2 and infinity. And so we get some small but pretty clearly non-zero numbers. It would be a big surprise if those points turned over and went to 0, right? So they're clearly headed towards some non-zero number. And better yet, if we take those extrapolations and then see what happens as a function of NC, we can see these lovely 1/NC² curves. So it looks like the masses of these particles, say for the lowest fermion, is 5.7 in these units, plus a very small number, 0.0034/NC², and that's essentially the right answer. The NC to the fourth and higher corrections are even smaller still. So this is really neat. We have this slight but non-zero NC dependence. It's one of the findings we had from DLCQ. So that's the story I want to tell you about DLCQ. If there's any questions here, I'll take them, but otherwise I'll head over to the Hamiltonian lattice. Okay, good. So a few years ago with Igor and Silviu and Benjamin, we worked out what is a Hamiltonian lattice formulation of the SU2 adjoint model, adjoint QCD model. And so what we'll do to build this Hamiltonian lattice, if you're familiar with the Schwinger model, right? On the Schwinger model, we have alternating sites that carry some different charges that change the gauge field as we go along. It's going to be a similar story here. These blue and green circles represent SU2 doublets. So these carry the SU2 charge of the fermions. You may be surprised that they're doublets rather than adjoints, but this is the way the group theory works out. If you form the Hilbert space of the adjoint, we can represent it in terms of these doublets. Then on the other sites, we have some SU2 singlets, and they carry information about the fermion parity of our particles. So it's sort of a neat separation of those charges, but this is degrees of freedom on the lattice. And then on links, as usual, the links carry the electric field information for the gauge theory, and they can transform in any irrep of SU2. So if you compare this to the problem we had before, right, where we had some SU2 adjoints that had to stitch them together with invariant tensors, it's an analogous but much harder problem. Now we have all irreps appearing. And so the way to deal with that is to use the more general invariant tensors of SU2, or the Clebsch-Gordon coefficients, to stitch together those irreps on links with the doublets on sites and build a gauge invariant state. And so this is how we build the Hilbert space for this model. And then you can also write down the Hamiltonian, and it also will be phrased in terms of invariant tensors. So here, for instance, there's a term that goes sigma z sigma. The sigma should be considered the invariant tensor on an adjoint and then two doublet indices. So the three matrices acting, three 2x2 matrices, that 3 and X is an adjoint, and the 2x2 indices are doublets. And so this can act on that doublet site. Then on alternating sites, it's also Pauli matrices, but for a totally different reason. So I've notated them differently, but we do have some Z and X matrices. But good, so this is the Hamiltonian. And so one thing you could do is explicitly construct a truncated Hilbert space for all these states, explicitly construct that Hamiltonian, explicitly diagonalize. One can do it. It is hard. I'll show you some of those results later. But another thing we can do, a la Benjamin's talk yesterday, is to build a matrix product operator and use tensor network methods. I won't say a ton about the details here, but I just want to emphasize that once one has the Hamiltonian from the previous slide, forming a matrix product operator is not really a ton more work. One has to draw a diagram like this, where there are some paths you can walk through to build these terms of the Hamiltonian, and then encode that into some matrix. But it really is sort of just this graphical restructuring. As Benjamin emphasized yesterday, if one has to solve a Gauss law to add the electric part of the Hamiltonian, that's a whole other thing, and that makes the matrix product operator more difficult. But Benjamin showed us yesterday how to avoid that step. And so we can really just use this matter part of the Hamiltonian, which has this nice periodic structure with all these chains forming terms. The details don't matter so much. What matters is that I could take that highlighted region and just repeat it like a unit cell all the way down my lattice, and I would get the correct Hamiltonian. And that's going to be the key thing that enables us to use not only finite tensor network methods, but infinite tensor network methods by making some assumptions of translation and variance. So this is sort of the core setup. It's going to go into several of the results I'll show you soon. Good. So what can we do with this? Well, one thing we can do here that we could not do with DLCQ is look at the data about the vacuum state. In DLCQ, one starts from a trivial Fock vacuum and loses information about, say, the expectation value of the mass operator in the ground state. But on the lattice, we just get a ground state and we can evaluate anything we want. And so we can compute, for instance, this expectation of trace psi bar psi, which enters the Lagrangian as a mass term. And so we did this first using exact diagonalization, explicitly building all those states, roughly hundreds of thousands of states for, say, a 12-site chain, building some big matrix, diagonalizing, similar in spirit to DLCQ, and getting this expectation value. And so we could see as we increase the value of n, it's converging more and more. And then we can extrapolate that to small values of the lattice spacing A. And that's what should give us the continuum limit in this picture, that small a. And so our first pass at this with exact diagonalization said it was ballpark minus 0.37. Now with tensor network methods, we can do much more. So we can go well beyond n equals 12. And now I'm showing you in green, n equals 32, 48, 64. Thanks to some nice work by Anna Maria. And we can see that the convergence is still happening, but this gives us a clear idea that it's bending a bit. And then the even cooler thing we can do is just jump to n equals infinity using these infinite MPS methods, relying on that translationally invariant structure of the Hamiltonian. And so just by jumping to that limit, then we can really extrapolate nicely to small lattice spacing and get a much more precise estimate for this quantity trace side bar side. So this is one new thing, qualitatively new thing we can do with the Hamiltonian lattice, and then we can do it much more precisely with these tensor network methods. Good. Okay. So what else? Well, we can try to look at the particle spectrum and compare it to DLCQ, right? We would hope these things should agree very well. So on a finite chain with open boundary conditions, one could evaluate the local Hamiltonian density on that interval, and it actually works out very nicely that you see this sine squared curve that you would expect from roughly a particle in a box. So it's a particle living in our box on the computer. And then by integrating this up, one could get an estimate for the particle mass at some finite lattice spacing, and then again extrapolate that to large n and a small lattice spacing. Or better yet, we could jump straight to the n to infinity limit using the quasi-particle ansatz that again Benjamin showed you yesterday on the infinite lattice. And so either way, we're seeing curves. I mean, it's better certainly for infinite n, but one can see evidence either way that we're headed towards this 5.7 number for, say, the lowest fermion that we had from DLCQ. So this is really encouraging that both methods are talking about the same theory and talking about them correctly. We see agreement for other states as well. This is an example of that. So this, of course, would give you a more precise estimate of the 5.7 number. I won't focus on that for now. Instead, I want to return those ideas of NC and sensitivity, right? Can we do this for SU3 or higher? And one can. The Hamiltonian model is going to look more complicated, but actually be quite analogous. So in our later paper, we wrote out how this generalizes to other groups. And so what happens is that doublet, the SU2 doublet, is replaced with a rather large dimensional representation. And then we have more singlets on these other sites. But the picture is schematically similar. So for SU3, for instance, we have octets on the charge sites, and then 4 singlets on every charge site, again, carrying fermion parity info. The Hamiltonian takes a similar form. It's more complicated, but quite analogous. We can build an MPO, can do infinite tensor networks, same spiel. One caveat, which limits our value of NC, is that one needs these 6J symbols. They're hard to compute. There's a very nice package in Julia that calculates them in a way that's feasible up to NC equals 4. In principle for any NC, but in practice, 4 is a pretty hard cutoff. So I'll only get there today, but I'll show you some results in a moment. So good. So all right. So say we had this SU3 lattice. What can we do with it? Well, we could compare some results to SU2. And here's a really surprising thing. Maybe in retrospect, not so surprising, but I was surprised. So if you try to plot, say, this mass of the lowest fermion as a function of lattice spacing before you do the extrapolation, again, we have this phenomenon where even at finite discretization, they almost exactly agree when the lattice spacing is rescaled by the Choate coupling. So I have NC G squared A squared on the x-axis, and then that mass on the y-axis. And we see these SU3 points are almost exactly inside the SU2 points, showing this very nice agreement, even on the finite lattice. So we can play the same game we played for a DLCQ and say, okay, why don't I take the difference at finite lattice spacing, where I have plenty of precision, and then extrapolate the difference. And the agreement's not perfect, but it's pretty good. So we see these black points are the estimate of the 1 over NC squared coefficient for that lowest fermion from the lattice. And then I've shown you the line from the DLCQ number. It looks like it's going to converge a little bit under DLCQ, which is maybe not so surprising if you're looking at those extrapolations earlier. They were going a long way. But nevertheless, same order of magnitude, within a factor of 2. So I think we're seeing the same kind of thing here, and we're getting it more precisely now. So we hope to extrapolate this even better in the future. So this is really neat. And that's for the particle spectrum that we had from DLCQ. What about the chiral condensate with trace psi bar psi? So this is going to be a yeah. So let me rewind a little bit. My current guess is that the culprit is these extrapolations. They're working pretty hard. So I would bet it's just a matter of that. I think the lattice will be the ultimate tool to give us a more precise number, but we're still working on grinding out our best possible numerics. But that's the story. Good. Thanks for the question. So now, how about the chiral condensate? So that's something that's new relative to DLCQ. Well, first things first, for SU2 and SU3, we have quite the same picture. I've shown you these points for the chiral condensate, rescaled as first done in this paper by Mutats and collaborators by the Triff coupling and then the dimension of the adjoint, NC squared minus 1. When rescaled this way, and then plotted again as a function of NC G squared A squared, we see the SU3 points falling right inside those SU2 points in beautiful agreement. We can see that the value seems to go a little bit past the exact number e to the gamma over 2 pi to the 3 halves from the Stringer model, but it was pointed out by Mutat and collaborators that these numbers are so close. We seem to see some daylight between them, but not much, which is a neat phenomenon, but separate to everything else. Anywho, that's SU2 and SU3. You might hope SU4 keeps the story going. But alas, if you look at the strong coupling expansion for SU2 and SU3, matches beautifully. In fact, they have the same strong coupling expansion. So by strong coupling, I mean large G times A. So you can think of it as a large lattice spacing expansion. SU2 and SU3 have the exact same expansion up to some order that we've computed. And the lattice points fall onto it beautifully. But then we also did this expansion for SU4, and it really kind of kills the vibe. It's the wrong sign and totally different. So what's going on? What happened to NC and sensitivity? This is disturbing. Well, the first thing we can do is try this on the lattice. So we push the lattice to NC equals 4, try to compute this quantity in the ground state. And it is reassuring for our ability to do strong coupling expansions, but not so much for NC and sensitivity. So it agrees with this expansion, but it's going somewhere totally different. So why is that? And here's where we can take a lesson from non-invertible symmetry. So in that paper I mentioned on my first slide from Zohar and Hand and collaborators in 2021, they show that in the SU4, in the universe I'm looking at for SU4, there are 2 vacua, not just 1. Strong coupling, we only see 1, but the belief should be that the lattice should find the other vacuum as we go towards smaller values of the lattice spacing. And taking some hints from smaller NC and playing some numerical games, I can actually get the lattice to converge into a not quite ground state, but oh so close. I can show you the energies later if you want to see. But they beautifully match on to that SU2 and SU3 curve. So this is this other state that I would conjecture is the other vacuum predicted by non-invertible symmetry. Moreover, this number where the other vacuum converged to for the chiral condensate seems to be not just some random number, but in fact predicted by their analysis. So they had this table of this OM is our mass operator, and they had a table where they gave ratios, not absolute numbers, but ratios for these expectation values in different vacua. And we can see if I assume the bottom SU4 curve follows SU2 and SU3 and hits this number below, take that ratio to predict the number above, it matches almost exactly. So this is a really nice agreement with that very non-trivial prediction from those people listed here regarding non-invertible symmetries. So this is really exciting. Preliminary, but nevertheless, I think it's pointing us in the right direction. Good. So let me wrap up. My larger point is that there's been lots of numerical progress on adjoint QCD2, and it's now accelerating rapidly, thanks in large part to the methods Benjamin showed you yesterday, using tensor networks and even infinite tensor networks to analyze these models. And so there's lots and lots of future questions, some of which listed here. One is for DLCQ, we had this lovely thing where at large NC, it was actually much easier and it took less effort. On the lattice, as far as we can tell, higher NC just gets harder and harder. One would hope there's some large N description that takes advantage of large N factorization that makes things easier. I think that's an important open question for us. In addition, what more can we learn from and about non-invertible symmetries? So hopefully we'll continue to match their predictions and hopefully also be able to just stare at these vacua and understand how the non-invertible symmetries are acting on our lattice states, or approximately acting, right? We think it's probably broken at finite lattice spacing, but softly so. And then, of course, there's lots more to do just in terms of mapping out the phenomena of this theory. There's an interesting SUSY point I haven't talked about at all. There's a phase diagram of the theory with multiple flavors, et cetera, et cetera. Lots more to understand and do, and we're looking forward to that. But for now, I'll stop there. Thank you. For giving us a very busy talk. And yeah, very positive.
There might be some hope to that many of these things are higher dimensional. Maybe not directly, but take the 3D theory is similar to circles, discretizing the circle with finding other points and then work with that. So it's not maybe something that occurred.
It's really not impossible. I think everything gets much harder, A, because more degrees of freedom, B, because the gauge field cannot be totally integrated out. So that adds a whole other, it makes it more interesting, but also makes it harder. So we're thinking about this, especially with regards to the tensor network methods. They might give us more room to grow there, but so far it's still a little ways out.
Want to bear in mind that that's not a absolutely.
Yeah, there's a long history of and yeah, Benjamin gave the sharp reason yesterday, right? For 1 + 1, one can do the contraction of the tensor network with a zero-dimensional boundary. 2 + 1, you're always going to have this system size boundary, so it just becomes qualitatively much harder. But nevertheless, yeah, we have hopes.
Is there a particular reason why you end up in when you do the naive S4 calculation, you end up in one of the vacuum as opposed to the second one?
Great question. So let me show you the energies of these things. And this also gives me a way to answer your question. So at strong coupling, we can label the states by the representations that appear on links. And we know it's a simple calculation that the one that has an alternating 15,6 is the lowest. That's just a fact. And you can see in this plot, right, as I go to large lattice spacing, that 15,6 in circles with a smaller energy. That's the reason we land on it. And that's the one that has the sort of other VEV. But you can see this one. So the way I've done the trickery to get this to converge into the other state is by noticing that in strong coupling, this 164 state has very similar VEV to SU2 and SU3. So the conjecture was that was the other vacuum. And indeed, the energies are getting closer and closer, suggesting that this is the case. But that this is how we do this.
I don't know if I should say this one.
Wonderful.
Before 2020, I think more or less the last serious work done on QCD2 about 25 years ago on Igor, David, and others. So in 2020, we wrote this paper in which we said that given the Vestas theory, all theories conventions complex. This is a big world. Through not only the Adjoint and others, the Schwinger model before the we wrote this paper. From my perspective, the estimation of Doha about this theory was related to that observation, the fact that the theory with all terminal vectors compound. So more or less all the discussion, new discussion that this theory started with that paper. And what Doha proved that these two marginal or marginally relevant all terminal vectors are forbidden by numerical, but they show that if you include them, the theory, Nestle's theory, confines. I really appreciate you referring to my paper with Theo and Stefano. I really appreciate it. But I think in the first page, the beginning of this discussion is not so much. The community gets it wrong. In this context, we are really discussing the item of QCD2. We are not discussing, more formal things. I think the paper should have been grateful for, not for me, let's say, for Yuya, Theo, and Alexei.
Let me, clarify. I certainly did not mean to. Well, thank you. Yeah, if I gave the impression that the story started with Zohar's paper, that was certainly incorrect. I wouldn't want to say that. The story goes back, a long ways to Igor's paper from the 90s. Where is Liam? Liam and friends at BU have looked at this theory with other methods. And then, of course, there was your paper from 2020. Yeah, the story goes back a long way, and that paper certainly kicked off a lot of this discussion and has done a lot for us. So yeah, absolutely. Yeah, thanks for the comment.
There are no more questions. Thank you once again.